That's again very encouraging. Because if you have only far field behavior, that we can say simply, no matter it is vibrating sphere, trembling sphere, breathing sphere, or vibrating circular piston, it behaves as if it is breathing sphere. If the volume velocity, that means how much fluid particle I am pushing out per unit time, is the same, then in the far field, what I experience, the pressure is the same. Doesn't really matter whether this is the type of source. Okay? Let me expand what we learned this case to more general case. And the Thursday quiz will include everything I will teach today. Okay? So on this z-axis, the sound pressure was quite understandable. But we do also want to know the sound radiation at certain point over here. Okay? And this integration on this axis reduces to very simple, because R is square root zeta square plus z square, and exponential jkr is simply z zeta square plus z square, and integration on this surface turns out to be what? 2 pi zeta and d zeta, right? And if I change zeta square plus a square to the alpha, change of variable, then we have this is alpha, and this turns out, this term and this term will cancel out, so we have a very easy integration that gives me e to the jkz minus e to the jkra, right? But what about the sound pressure at this point? It's not symmetric anymore. So let's look at sound radiating from this sphere on Z, and did I use X? What kind of X and Y coordinate I use? And my assistant skipped that picture by some reason, so I have to look at you omitted the figure 4.2.4. Figure you don't have it, right? You don't have it, right? Right. Very sorry, and we will provide the figure for everybody. In Korean text we have, but in English version it is gone. Suppose I have x-axis here, and the y-axis here, and I have a vibrating piston. Okay. Now it is no longer symmetric, so I have to consider ds, the surface of integration over here. Then I denote this radius zeta, and the angle between x-axis I denote phi. Okay, and I have observation points over here that I call R0 vector, and this is I call R, and this is small r. So I have, this is right angle, and I call this is zeta. And I promise I will not ask you derive that equation in the quiz, so don't worry about it. I'm not that kind of very bad professor. I want you to understand the physics along this vibrating sphere case. Okay, in the text you can see very detailed derivation, and frankly speaking, I cannot derive in by myself right away. I have to look at it. Huh? If you ask me, I would try. But it's a very tedious calculation. But before we start to do it, let's explore physically what would happen, the sound pressure at this point. Does it depend on phi? If this piston is vibrating uniformly. Suppose we have a piston, and the phi is the angle over here. Okay, piston is radiating this way. Does it depend on phi? Anybody think it depends on phi? Raise your hand. Is this your, no? Itaeon, you had a hard time last night, so you but it should depend on theta, right? Okay. Okay. In fact, the radiated sound depends on interesting mathematical form. That looks familiar to you guys, right? Huh? What is J1? Bessel function, famous Bessel function, first kind, right? Huh? How does it look like? J1. What is the value of J1? 0. J1, 0. 1 or infinity? Nobody knows? Okay, that is another possible candidate for the Thursday examination.